Hello everybody and welcome to exercise 2 on page 26 of the workbook. And let's read this question together here. So they're telling us the amount of electrical power drawn by a household is given by F of t kilowatts, where t is the number of hours after 6 p.m. So we're thinking of 6 o'clock p.m. as representing the time t equals 0 in our problem. Okay, and the values of the function, the powers, are actually given over here. Okay, so no formula, just a table of data for us. And part A would like us to use the trapezoid rule to estimate the value of the integral. Okay, and they're pointing out that this integral is actually giving us energy usage between 6 and 9 p.m. Remember again that 6 o'clock p.m. is time 0, and so 3 hours later would be 9 p.m. Okay, now this problem's a little different than some of the ones that we did before because we've got a table of values instead of a formula. Okay, so I'm going to just draw a picture to maybe help us draw the connection here. Between 0 and 3, that's the interval that we're integrating over. They don't tell us a value of n in this problem, which means they're expecting us to choose the value of n ourselves in a way that's reasonable based on our data. And notice that we know the power at 4 points, 0, 1, 2, and 3. And so that tells us that it's kind of natural to chop this interval into 3 pieces. From the picture, what that means is that delta t is just going to be the width of one of our intervals. We can see that from the picture to just be 1 in this case. We don't need to calculate it, we're just taking it from the number line. Okay, so that means that when we do this estimation for T3, okay, we're going to start with the same formula for the trapezoid rule that we've been doing. We're going to get delta T over 2. And then the trapezoid rule formula works by just taking our actual partition points and plugging those in. Okay, so we're going to get f of 0, and then the middle numbers are going to have 2's in front of them. So plus 2 f of 1, plus 2 f of 2, and then finally plus f of 3. All right, can we find numbers for these things? All right, well, we already noticed over to the right that delta t is equal to 1 from the picture. And how do we get these function values? Like f of 0, for example, how do we figure out what that number is? Okay, well, really, we just need to look at the table. F of 0, by definition, is 2.15. Okay, and then we move on to f of 1. That's also in our table. That's sitting here. That's 1.52. And we just keep going. F of 2 is 1.10, and then finally f of 3 is 1.02. Okay, and once we're here, just a matter of adding that up. So going to your calculator, what you should come up with there is 4.205. And the only remaining question is, what are the units? They asked us that. Okay, how are we measuring the energy? Okay, well, again, we can answer that question like that by looking at what we're integrating. So we've got f of t. What units are f of t being measured in? Okay, well, they tell us kilowatts up here. And what units is time being measured in? Hours. Okay, so if you take those two units and multiply them together, you get kilowatt hours. Have you ever heard that unit before, kilowatt hours? Okay, that's a unit of energy, and you may have seen that on your electric bill. That's you pay for the number of kilowatt hours that you use. Okay, and so then part B just asks us a question about the estimate, the accuracy of our estimate here. That 4.205 kilowatt hours that we just came up with, does that represent an under or an overestimate of the amount of energy used? Okay, well, the only way that we really have to answer a question like that is graphically. We know that it has something to do with concavity. So one way to approach this is just to make a little scatter plot. It doesn't need to be terribly accurate. But if you take this data and just plot it, okay, and this is going to be a very rough sketch. Okay, 1, 2, and 3. We'll put 1 and 2 up here. Let's see, at t equals 0, and I'm looking back up at the table here, we get 2.15, so we're a little bit bigger than 2. And then we jump down to 1.52, that's maybe about there. 1.10 is maybe about there, and then 1.02 is maybe about there. Okay, and if you connect the dots here, try to draw a smooth curve, what does that look like to you? Concave up or concave down? Okay, if I had to guess, I would say that looks slightly concave up. Okay, and if you look back a couple of pages, we made the observation by drawing in some trapezoids that if a function is concave up, the trapezoids are going to be above the curve and therefore give us an overestimate. Okay, so let's say it this way. Since f appears to be concave up, okay, on the scatter plot that we just drew, our answer to A should be an overestimate of the energy used. Okay, and I think we're done.